a great turnout for this event. I'm Dr. Brian Monacelli. I want to also give credit to the scientists that are part of the Sherlock instrument, particularly Dr. Bartha, who put a lot of this presentation material together with me. So I'm an optical engineer. I'm also a technical group supervisor, which means I mentor and supervise different levels of engineers at JPL. And I've been working on a number of instruments, and my job is the hardware. I am fortunate to actually put parts together and join projects where the rubber meets the road and we actually build instruments. So I'm going to talk about the instruments that I built on the Perseverance rover. I actually have a solid model of a real size model of the Sherlock instrument here, and I also have some spare flight components that you can see and maybe come up here and hand around. So without further ado, I'll get into that. This is the Sherlock instrument. So that picture was in our clean room before it left JPL, and when it gets to Mars, things get dirty. And we're trying to do science on another planet. So you might imagine that cleanliness, when we're measuring things, is paramount. So here's just a good example of some of the challenges that we had in addition to cleanliness. So our instrument is out on the arm of the rover, and I'll show a picture of the whole rover and where we're located in a moment. But being out on the arm of the rover is actually a very difficult challenge for the engineers, not just because we have to place an optical instrument that has to, look at the rock samples, much like Sherlock Holmes, which we were named after. So we have a magnifying glass out on the arm of the rover. We have to actually place that arm very accurately. We have to be able to place that to millimeter level accuracy, and this arm is about 3 meters long, and it's able to position on the order of 400 to 500 pounds. I'm not exactly sure of the mass, but on that order accurately. So next time you're at the gym, grab a 50-pound weight and try and position it to about 3 meters or millimeters in accuracy. So the placement uncertainty is actually a huge deal for this. Whenever we're doing any kind of science, we want to be able to know what it is we're measuring. The other issue associated with Mars is, if you're familiar with Rocket Man, Elton John got it right. Mars is cold as hell. And we really have to deal with the fact that the Martian environment on its warmest day is about the temperature of this room here. And typically it's extremely cold. So all of our objects have to survive this temperature, and also has to survive, as we said, as I said earlier, a high dust environment. So everything's very, very dirty, and we're trying to do very precise science on Mars. We have a number of different things on the rover that we tried to clean before they left Earth. We tried to allow them to what we call off-gas or out-gas, which is to remove any kind of volatile chemicals. And even the best efforts to not remove everything. So during cruise, we have a number of different contaminations that we impose on ourselves. We self-contaminate, in a sense. And we're going to do this for, and this is kind of a fun one, we're supposed to do this over 1.25 Martian years. We're actually just started our third year on Mars. So we're excited to have functionality for longer than expected, and we expect it to go a lot longer than this on Perseverance. So we have a number of different deployments. This many analyses have been done so far, so it's almost 300 analyses of different Martian samples. And what this instrument is really doing, I'll talk about in a moment, but these are just some of the challenges that we had as we went into it. So I want to highlight one of the challenges. This picture was taken from the sky crane. So as Perseverance descended down onto Mars, when we went through the atmosphere, we have to decelerate. We have to slow down. And to do so, we actually drop down on a parachute. And as it's coming down, you might imagine it's a bit of a turbulent ride. And so out here is Sherlock. And that's the amount of dust that we got just between the camera and the parachute that's holding the rover and the instrument itself. And in seeing this imagery, after having built what was one of the cleanest instruments that JPL's ever built, I was a little concerned. So we survived that, and we were able to land down on Mars. We were able to actually take imagery of the Martian environment. We were able to say, yeah, there's still more dust coming. So we're going to continue to be covered in dust. And if you've seen the feature Good Night Ophias, anyone ever seen that? It's a newer film out there about the Opportunity rover. Opportunity was actually lost because a dust storm covered its solar panels in dust, and we were no longer able to adequately power it. So it was heartwarming story, but that was a big part of the reason that instrument went down. So dust is a big problem, and we're trying to do geological science. Just to kind of orient you on Mars, if you're familiar with any Martian geography, there's a number of different craters. We are settled in the Ventura crater is the landing site. Just to show you where some other instruments are, the Curiosity rover, which landed in 2012, is over here. The InSight rover, which landed in 2017, I believe, is right next to that. That is a lander, not a rover, so that actually has a seismometer on it. It's measuring Mars quakes. And then there's some Chinese instruments, rovers there. Viking, some of the first explorations of Mars aren't too far away on the Martian surface. So our goal here is to measure the Martian geology. We want to study the evolution of Mars over time and perform this geological science in something that we believe and we have measured to be the presence of some of the oldest rocks in the solar system. So Mars is like Earth, a rocky planet, and we're looking for some of the oldest rocks on the planet. So we looked in what basically looks like a river delta. So this is effectively what New Orleans may look like in a long time from now, where we have the Jezero Delta here. And so we landed on Mars. We landed within a kilometer of where we intended to land. So think about that. It's a pretty long shot to Mars, and we were able to hit that target very well. This was our circle target. That's about where we landed. And the goals of this mission to go to Mars is to perform the geology and search for signs of what we call astrobiology. So we're looking for signs of life. Sherlock is, in essence, a life detection system. And I'll show you some of the science behind the life detection processes that Sherlock employs. And when we find something that's particularly interesting, this rover has an amazing feature of being able to cache it because we're very ambitious at JPL. And we want to send an instrument back to Mars and collect those samples. We want to do a handoff on Mars, self-assemble a rocket, launch it to a rendezvous vehicle, and bring those samples back to Earth. And that's a mission called Mars Sample Return. It's a mission that's ongoing right now, and something that we're very excited to be developing, hopefully to launch towards the end of the decade. I don't want to sign my colleagues up to any particular time for that yet. But the other really interesting thing that Sherlock has a very dedicated role in is the opportunity to learn how we can prepare for human interactions on Mars. Now, there are many other instruments on the Perseverance rover that are doing this, but Sherlock in particular is studying the spacesuit materials and the degradation of those materials in order to determine how they will survive and therefore how they will protect us as we travel to Mars. All right, so this is the rover itself. It has a number of different instruments. I like to compare this to the previous rover, Curiosity, if you're familiar with that. We upgraded this instrument sort of like going from a Honda CR-V to a Honda Pilot. It's a little bit bigger, it's got some more features in it. It's a heavier rover, but we have 7 times the science. We have 7 more science instruments. We have 23 cameras on this. And many of these, as an optical engineer, I was fortunate to actually interact with the optical hardware directly. But I'll talk first about the non-optical hardware. RimFax is actually a radio frequency penetrating radar. So it goes down into the soil and actually looks directly beneath the rover, and that's able to do that in the radio band. I talked about studying the possibility of having humans survive on Mars. Well, to do so, Mars is primarily carbon dioxide. So what we want to do is take that carbon dioxide and change it into the oxygen we need to breathe. And that's where the MOXIE instrument comes in. So this uses a technology that's very similar to the technology they use in submarines, nuclear submarines, to actually convert abundant carbon dioxide into oxygen. So I'm not an expert in that instrument, but I do know that we have successfully produced as much oxygen as a small tree would have produced on Mars. So that's our metric. We measure that in trees, much like your solar panel report may come in, how many trees you've saved. So we have produced a tree with MOXIE and it's still going strong. META is a really interesting instrument. It's actually a weather system. So we're actually measuring the transmission of the Martian atmosphere. We're looking for clouds and other formations like that. And then Mastcam Z and Supercam, there's a number of different pictures that you might see. This is the binocular vision when we get the 3D pictures back from Mars. That's done with Mastcam Z and Supercam. We also have a spectrometer in that part of the rover as well. But I'm here to talk, oh, before I forget, our friend out here on the arm of the rover is Pixel. This is an X-ray lithochemistry instrument. Pixel looks for elements. Sherlock looks for chemicals and molecules. Okay, so combining the X-ray technology of Pixel with the molecular chemical technology of the ultraviolet radiation that Sherlock emits, we're able to cover a very broad spectrum of the chemicals and analyze many different types of samples. And of course, because they didn't make it hard enough by building this on Mars or sending this to Mars, they attached these very precisely aligned optical instruments to a drill. And many mechanical engineers would say, wow, that drill, that's a precision polishing machine. We can abrade surfaces to almost mirror-like finishes. And to an optical engineer who puts this instrument together, it's a jackhammer. It's shaking around the optical instruments quite a bit. And so that's always been a challenge, an interesting challenge, to understand the dynamic environments, not just the thermal environments, but the dynamics that this instrument will have to see. And if anyone's familiar with the Sherlock Holmes story, Sherlock's companion was Watson. So we decided to name the Molly build-to-print imager. Molly was the selfie camera from Curiosity, so we made another one because it worked really well. And we put it on Sherlock and we renamed it Watson. So Sherlock and Watson work well together. And I will show this in more detail later, but this is the size of Sherlock. So this is out on the arm of the rover. The Sherlock instrument's primarily here. The electronics are on the back, and I'll talk through all the optics inside and the instrument itself. And this right here is friend Watson. All right, so here's the Sherlock instrument. We do what's called deep ultraviolet fluorescence in Raman spectroscopy. So if you're familiar with glow-in-the-dark objects, it's basically causing fluorescence. What you're doing is you're exciting it with a short wavelength of light, and it's causing the material, the fluorescent material, to emit longer wavelengths. And based on the colors that of the material emission, you can actually identify the material itself. And that is the process of spectroscopy. Now, that's the fluorescence part of Sherlock. The Raman part of Sherlock actually looks for vibrational modes that are excited in the material. And those vibrational modes are indicative of the chemicals that are the building blocks of life. And I'll get into that in a bit. All right. Our Sherlock laser excitation is at 250 nanometers, so very deep into the ultraviolet. This is beyond the ultraviolet C radiation that would give you skin cancer and very bad sunburn. So quite a ways in the ultraviolet. We also have the ability to take images, context images of what it is we're lasing on Mars. And then we, of course, measure the spectrum coming back from that. So we've done this with a very few number of isolated optical systems. We've actually allowed each system to be developed independently, and we worked with 5 different independent contractors to do this, and we integrated them all together. And I was the fortunate person to be the lab lead to build all these pieces and integrate them into this amazing instrument. And of course, whenever an engineer or anyone technically savvy has something interesting to show you, they always take the hood off the car, right? So I'm going to take the hood off Sherlock, and in fact, I can even do that with the solid model here. So if you want to come up later, we'll actually show you what it looks like under the hood. What we're doing with Sherlock is to emit this laser signal out of our deep ultraviolet laser on the bottom here. We take it through some conditioning optics. So the laser comes out the side here, goes through some conditioning optics, and what this does is it cleans up the laser signal. If you've ever worked with a laser, even just this handheld laser, there's actually what's called a background plasma glow to the laser. Particularly gas lasers have this emission. If you're doing any kind of astronomy, you can actually see all of the different spectral lines of different chemicals that you're looking at if you do any kind of spectroscopy of the distant stars. And with a laser, what you're doing is you're choosing one of those colors. You're choosing one of those spectral lines to be the color that lasers, usually the most intense color that comes out. And so first thing we do is we clean up the laser, we get rid of those other colors, we only send out exactly the color we want. The laser then bounces around and it goes off of a scanning mirror. I've been remiss, I have not even told you what SHERLOC stands for. SHERLOC stands for Scanning Habitable Environments. Scanning habitable environments using Raman and luminescence for organics and chemicals. Okay, so a lot of these acronyms at JPL were made with imagination and sometimes a dose of whiskey, because you need to really get all the technology into the term that you really want. And what we're actually doing with this laser is we're scanning. So the scanning mirror actually tips and tilts the beam around and causes a raster pattern to be formed on the regolith, the rock formation that we've now ablated and drilled away. So we've created with our drill this beautiful sample of the Martian soil by putting the arm down on the soil, caused a perfectly nicely flat sample to be measured, and then we're actually going to shine the laser out this objective. So this is really no different from Sherlock Holmes' objective lens. It's basically just focusing down the laser at the proper distance. Sherlock instrument is able to focus between 40 and 60 millimeters away. So it's adjustable focus. So we have to get pretty close, and we have to be able to hold that arm with the rover to sub-millimeter accuracy. So that's very difficult to do. But it is an autofocus objective, and we're able to take images as well. I'll show you the imaging path also. When we had an error with the scanner, we actually had a joke that we're going to have to change Sherlock's name to Sherlock and send Sherlock to Mars. But fortunately, the scanner is quite functional and doing really well on Mars. So after it goes off of the scanner mirror, comes out of this objective lens, focuses about 2 inches or 50 millimeters away, and is able to excite the Martian surface. The other thing we decided to do was to co-align one of the highest resolution imaging systems that we've ever flown to another planet. Because we want to see in context where it is we're shining the laser. So if we're shining the laser here, we want to know what it is, the region we're mapping it over. So we have also a context imager. This is a visible light context imager. It operates from the green to the red part of the spectrum, and it produces images about the size of your thumbnail. Okay, so really, really small images with 100 micrometer resolution. So if you have hair, you just reach up and grab it. Your hair is about 150 micrometers in diameter. So we're able to focus the laser down to about 100 micrometers. Out of Jezero, so here this is just the edge of Jezero. This was the landing site. So you can actually get an update of this if you search for where is the rover. So just in any search engine, search for where's the rover, there's a map of this now, and actually now it's updated to show all the points along the path where it's cached samples. And I think we're up to 18 samples that have been cached now. So this is the Ingenuity rover, so the rover's right there, and Perseverance is making its way up the Velvet Crater and studying the delta. So just these are a couple of the cache sites there. And so what I'm going to show here is just some of the science data. This is actually early science data. None of this has been published in a peer-reviewed science journal. So this is something that I think this is one of the few times this has been presented actually, because it's now just being peer-reviewed as something that we're able to study what chemicals we found on Mars. So talked a little bit about this already. Mastcam-Z and the navigational cameras, NavCams, they study at the meter scale. SuperCam can get down to centimeter levels, but Sherlock and Pixel can get down into the microstructure. All right, so we drill these holes into the microstructure, or into the Martian soil, and look at the microstructure. And I'm just going to kind of zoom in on this. One of the nice things about Watson, if you've ever seen those CSI crime show TVs, you know, they always have these great pictures and then they say enhance. And of course you can see the detail because it's TV, right? We can actually do that. We can zoom in on it. So we're able to zoom in, we're able to create these images. Remember, the resolution of this image is 10 micrometers, and this is some of the highest resolution imagery that we've taken off of Earth. So this is what it looks like as we zoom into the different rock formations at each of those points I showed in the previous map. So here is the native rock before we abraded it, and then when it has that circular structure, this is what it looks like after abrasion. And we go down into the imagery, and now we're able to actually map the chemicals that are present there. So this is just some of the preliminary mappings that we're able to do. These are the survey scans. As I said, low pulses per point. So only 15, we go up to 500 when we're really trying to get good science out of this. So these are just some of the images that we show here, and this is what the spectra will look like. So these are the high dynamic range scans. These are the 500 pulses per point. And each of these represent a different point that we have pulsed. And as you can see, all these rainbows, all these plots look a little different, okay? So when you're viewing these plots, think of this as a rainbow. I know this says Raman shift, but it's appropriate it's related to the wavelength or the color coming off of this. So this is kind of the violet end of the rainbow. This is the redder end of the rainbow. And when the spikes are higher, that region is more intense, okay? So by correlating this back to a database we have on Earth, we can map out what every single point we've hit is made from. And that's the power of spectroscopy. And that's why I think spectroscopy is one of the most important scientific developments of the last century. You can hit something with light, or just study the light naturally coming off of that something. Look at the characteristic rainbow and be able to determine what that something was. What was that material? You can probe this. And this was very important during the pandemic. If you ever been in a medical facility and you sent a sample to the lab, guess what they were doing? Spectroscopy. Okay, so a lot of this is pervasive in our life, and we're able to do this now on Mars with extremely high resolution. So here is an example of some minerals that we're able to sense. So quartz, topaz. Honestly, not a lot of surprises yet. We did sense some abiotic organic materials, meaning without biological signatures. So we were happy to find organics on Mars, but they were not biological in nature. So Sherlock satisfied the O part of its name, but definitely not a life detector yet. And here are just some of the other spectra. These are actually measured spectra that we're able to measure and compare to what we found on Mars. So this is a particularly interesting part because it looks like a polar bear, so it got a name, of course. I don't know how many of you have done this, but you look at imagery from other planets or even in the stars, and you draw constellations, basically. So that's what we did. We drew a constellation here, and decided that this looked like a polar bear, and we're able to actually map out the chemical compositions of the polar bear here. So each color here has been color-coded to different types of chemistry that we're able to find in the rock. And so Sherlock is an effective mapper. It has proven itself as a tool that we can use to actually map out how the Martian geology has evolved. And here's an overlay of these images on the main map. And again, these images are about the size of your thumbnail. So we're really getting down into the dirt of Mars. So that said, that's the discussion I wanted to present to you on the Martian exploration of Sherlock. I'm happy to take any questions. This is our little fist pump with the Sherlock instrument on Mars and some Martian mountains in the background. And we were really happy to see this, of course, as engineers that worked on it. Actually, when my colleague sent me this image, I was outside and saw Mars in the distance. And that was a pretty heartwarming experience for me. So my email address is up here. If anyone has any questions, I certainly welcome questions. I'm going to show the model here, and I'll allow you to kind of come up and interact with it if you'd like. I also would be remiss to not mention that I'm also a professor. I've been teaching for about 15 years, technicians, hands-on skills. And as I said, I'm one of the few people who get to work with the hardware and actually build it, especially as an engineer. All the time engineers need skilled technical help to do this. So I know Moorpark College has a good astronomical program, correlations like that. So if you're doing any kind of astronomy, you want to understand the instrumentation. I teach at Pasadena City College, and I teach how optical systems are put together and how they're built. And I have some flyers for that in the back if you want to learn more about that and how to actually do the hands-on work But that said, I consider all of you my students, so please feel free to drop an email to me at any time and ask about optical instruments and how they work. And then I'm open to questions, and you can also see the model. So, thank you. So I know that's a very common. It's actually an interesting kind of double-edged sword. We have this philosophy called heritage at JPL, which means if we've proven something to work, we're going to probably try some aspect of it again. The sky crane maneuver, where we did the entry, descent, and landing through the Martian atmosphere, that was a fantastic success with Curiosity, so we did it again, and it was also a success with Perseverance. So the landing techniques were remarkable. In fact, we beefed up the parachute for this one. We put a coded message into it. We added more cameras to that because we wanted to see actually what was going on. So I'll give you an example of what was not a good idea. And this is kind of me talking off the cuff. I don't know if this is released information, but this is the objective lens. This is basically the same lens that Sherlock Holmes uses. That's inside this focusing mechanism here. So this objective lens goes in here. Okay, and this is one that, this is the tube for it. It's actually a 3D printed aluminum tube. We just tried it as a prototype. And this is one I aligned by hand to see how well I can do it. So this is actually a little magnifier. And as you might imagine, this is about 20 millimeters in diameter. When you're working with spectroscopy systems, you actually want to take in as much light as possible. You want to see a lot of different photons. That way you can study all the different spectral bands that might be present. But we had the heritage of Molly, Mars hand lens imager on Curiosity, which we love so much because it works still so well that we rebuilt it in Watson. And they said, don't change that package. That package worked really well, and this mechanism is phenomenal. So let's do it again. Let's put that as the focusing objective on Sherlock. But now we're only able to expand our optics to 20 millimeters. So this on the imaging systems like Watson uses very small lenses that operate much like a cell phone lens. Okay, they're wide field of view lenses, so the optics kind of go through a focus in there, and you can get a wide field of view. We had to blow out this lens tube to its maximum diameter, such that these wall thicknesses, you can see it when you come up here, are on the order of 1.5 to 2 millimeters. So very, very thin wall thicknesses. And then I invented a technique to actually hold the lenses in there and then articulate them in 5 degrees of freedom, bond them in place to put 4 lenses in here. So that was a remarkable challenge that we had. And it was, as I said, a double-edged sword. The heritage was that the camera and the mechanism worked really well, but that packaging, that form, doesn't cater to spectroscopy as well as we want it to. So there's just one example of that. So we have a lot of that on evolution of the instruments. We kind of take what worked and we meld it into the best possible solution for the next generation. Yes, there was a cruise vehicle. Yeah, so here's the laser on the bottom. The light comes out here. This is a beam expander. It blows up the laser to about the size of it comes out, so about 12.5 millimeters. And then that reflects off of this mirror. And then it goes. So then the light comes out of this. It comes back in there. It's the same path. Goes off the scanner, and then goes into this instrument. This is a spectrometer. So I don't have a lot of spectrometer optics here. But the size of the spectrometer, this is the back of it, it's about the size of that blue rectangle you see there. Okay, so that rainbow that I showed there is actually extremely project. Put all the electronics on the back side. So multiplex. So what this does is it takes the image from Watson, which is a zoom image, it takes the image from the Sherlock context into this system, and it allows them to be overlaid electronically.